This is the second part of section 1 of chapter 3, simulation principles. So as you remember, we had the example of Able Baker call center in chapter 2. So here we want to define these elements in order to formulate the system in terms of a discrete event simulation model. Okay, so the system's state, here we define 3 state variables, and the collection of these 3 variables will describe the system's state at any time. So LQT will be the number of colors waiting to be served at time t. Okay, so and LAT and LBD will be the Able and Baker's status at time t. So it's a binary variable. So 0 means they are free and 1 means they are busy. Okay. For the entities, yeah, as you know, we have entities here. The colors and the servers are the system's entity, but here actually we don't need to explicitly represent the colors, even if we are interested to have a certain color averages, for example. So in this case, we'll have in general entities actually, but since all are common, so we don't need to actually explicitly represent them. So because of that, we won't have attributes here, right? Yeah, we don't have, because they're all the same. They are not going to be individualized in the system. The events, here we have 3 events that change the system's state: arrival event, service completion by Able, and service completion by Baker. Okay. And the activities here, we have these time durations or activities: arrival time, service time by Able, and service time by Baker. Okay, and the delay here, we have a colors waiting time in line until Able or Baker becomes free. So we have this time duration as delay, not activity in this system. Okay. So as I said before, I can say the core of a discrete event simulation is its event scheduling or time advanced algorithm. So here we'll have a mechanism in simulation in order to guarantee that all events will occur in their time in chronological order of the events. So here we will have a feature event list, and we will order chronologically the feature events in their occurrence time, and then based on that we will actually process the events. Okay, so at the instant of beginning an activity, for example, interval time or service time, its duration is obtained based on the distribution, or let's say the data that we have for that purpose. And the end activity, I mean the end of the activity, it will be an event, and that will be included in the feature event list with its occurrence time. Okay. So at time t, we will have a feature event list, and they will be ordered chronologically in their event time. So here t1 actually will be the next event that will be occur, and we call this as the imminent event. Okay. In a discrete event simulation, as time advances, the system state, as you see here, the FEL, feature event list, and also the statistics that we have defined to measure the system's performance at the end of the simulation, they will be managed in a table like this. So as you see here, at any time t, we have the system state by the state variables. We have the lists, for example, then the customers who are waiting in line, the customers who are being served right now, and we have the feature event list as here. The next actually event will be about the entity number 3, and its time will be at time t1. T1 is greater than or equal to t, the current time of simulation, right? And also here we'll have the cumulative statistics and counters. So this is how actually we show the mechanism of time advance in a discrete event simulation model. Okay. So here we have the algorithm for the event scheduling. As you saw, we have an imminent event, right? In the future event list, the next event that's going to be happen. So as step one, we remove the event notice for the imminent event from FEL, and then we advance the time to the event time of that event. So time will be advanced at that time, and then we execute the imminent event. So it depends that what's the type of the event. If it's arrival, so we'll see how the state variables will be changed by this event, or if it's a departure, again we'll see how the state variables will be changed. So when we say execute, we mean we'll process the impact of happening of this event on this system's state. Okay, and then generate the future event if necessary. For example, if it's an arrival, then at this time we will generate an inter-arrival time for the arrival of the next entity, and that event will be again included in the future event list with its time. Okay, and then at the end update cumulative statistics and counters. Okay, so this process repeats until the simulation is over. So as you see here, the core part of a simulation model is the event scheduling or time advance algorithm. Okay, and the stop event of the simulation is also obtained and included in the future event list as well. Okay. Here we have a method called bootstrapping for generating external arrival stream of entities to our system. Here, anytime that an arrival happens, we'll generate an inter-arrival time, let's say a star, and then its event time, I mean the arrival time will be t star, will be this t plus a star, right? So t is the current time and a star is the inter-arrival time for the next arrival. So the next arrival will happen at time t star, right? And then we put this event arrival with its occurrence time t star in the FEL. So this is called bootstrapping, and by this method actually we generate a stream of arrivals over time for our discrete event simulation model. Okay. So for example, let's say we are at time t and it's the arrival of nth customer. So at this time, we generate a star, the interval time for the next customer. So the customer n1, n plus 1 will arrive at time t star, which t star equals t plus, I mean, the current time plus the a star, right? So this is how the bootstrapping method works for the time advance algorithm. Okay, so this is actually the time advance algorithm, and in the next part of the video you will see how we apply this algorithm in an example. Okay.